Thank you. Thank you. First, I would like to thank organizers for inviting me for this very nice conference. And before I start my talk, I also want to thank my students and our lab technicians for their work, which made possible this work, which enabled this work, as well as our funding sources. Today, I will talk about ergodic, which is history dependent, and non-ergodic, which is non-history dependent of charge carrier dynamics at the atomic length scales. And as a disclaimer, I can tell you that this talk is a little offspring compared to the main theme of this conference, at least this session, because it has nothing to do with the spins and or magnetic materials, but we are more concentrated on inorganic materials. So the very first question is that why we are interested in inorganic oxides. First of all, they have their material properties are tunable. Particularly, we can tune their electronic properties without changing or without sacrificing from their other properties, such as their chemical properties. And they are ideal substrates for high temperature superconducting films, for instance, iron selenide films. And they can be used as substrates for complex oxide epitaxy because of the ideal lattice match with other materials. And they have a wide range of applications for renewable energy and electronics applications. In addition to that, the next question or the next logical question that we can ask is why we are interested in time result characteristics. By measuring time result characteristics, we can reveal the charge carrier dynamics, which are the dynamics of electrons, holes, or vacancies in the materials, which carry charge from one location to another. And we can measure these charge carrier dynamics with spatial and temporal length scales. And of course, by measuring these two, we can reveal local defect energy barriers, which may be interested for spin-based materials for you, and effective activation barriers, which is like the effective activation barrier for one vacancy or one charge carrier to move from one spot to the another. And we can look at these properties as a function of surface and or bulk defect density. Of course, this looks cool, and this may give us some interesting physical or chemical background, but the question is, how can we measure time result properties? I believe majority of you has used or has at least heard about atomic force microscopy. And when we talk about atomic force microscopy, there are basically two different modes. And majority of the people are interested in amplitude modulation, which is based on the measurement of the oscillation amplitude and demodulating the tip sample separation by using these two. And this is a mechanical technique, and it has mechanical limitations, which is like it scales with the quality factor of the oscillating probe. For this reason, the obtainable time resolution is limited within the order of seconds or half a second. In the order of seconds is the right term. The next modulation technique that can be used is frequency modulation, which we can modulate the tip sample separation by demodulating the resonance frequency shift of the atomic force microscopy cantilever. And physically, there is no mechanical limitation for this technique because frequency shift is an instantaneous phenomenon. There is no time delay between these two. And when I began to work on the institute, we unfortunately didn't have any microscope that was capable of achieving this, and we had to do some engineering, and that part may be interesting for you as well. And we had a Vico enviroscope scanning probe system, so it's a very generic atomic force microscopy system. If you ever use atomic force microscopes, you probably has used something like that, which is pretty good for topography measurements, but the main challenge for us that we want to enhance the system, and we wanted to integrate frequency modulation capacity in order to conduct time result experiments with this system. So the regular control architecture of AFM, probably if you use like AFM under, it has a control architecture something like that. You have an oscillating probe, and then you demodulate the oscillation amplitude, and then you control the tip sample separation by working on this control of the oscillation amplitude. However, we wanted to implement frequency modulation, which means that we wanted to get the instantaneous frequency shift of this oscillating cantilever. So we had to employ some others, we had to integrate some other control hardware to existing hardware of our atomic force microscopy system. To be able to do that, we had to have actually a second controller which works totally independent from our existing controller. And then we had a separate lock-in amplifier to modulate our resonance frequency shift and oscillation amplitude and phase, while correcting and automating the experiments with MATLAB and Python algorithms. So there was some engineering to some extent in order to enhance the capabilities of our microscope. And as I mentioned, in order to conduct time result measurements, we had to employ MATLAB for resonance frequency shift corrections, as well as Python to automate our experiments. So after this upgrade part, which may be interesting for you if you want to do something beyond topography measurements with atomic force microscopes, we were able to do time result measurements. And we conducted time result measurements by applying electrical pulses, between our cantilever probe and sample surface. And when we apply the electrical pulse to our material, we actually create an electric field within the proximity of the cantilever. And when we create this electric field within the proximity of our cantilever, we have a time-dependent Coulomb interaction within the surface. And the collective motion of charge carriers, which can be electrons or holes within the material, are reflected as time-varying force, and this force can actually be demodulated as a resonance frequency shift. So it's actually quite simple in that respect. We apply a pulse, electric pulse, and we just measure the resonance frequency shift. And this resonance frequency shift is due to the time-dependent change of Coulombic interaction within the surface. And when we did something like that, we were able to actually get the effective activation barrier of strontium titanate. And we conducted this experiment with spatial resolution, and we conducted this measurement as a function of temperature. So when we conducted this measurement as a function of temperature, it was possible to get the effective activation barrier by using this Arrhenius plot. And as we did this experiment as a function of with a spatial distribution, it was possible to get at which parts of the surface we had longer time constants, at which parts of the surface we had slower time constants. So we had some sort of spatial distribution, and it was possible that we also get some indication that either strontium or titanium terminated surface had difference in their time dependent characteristics. So on top of this, we also looked at the temporal variation of the measurements, which means that we also looked at the history-dependent effects. So here, it's very similar to the very first experiment. However, we changed the delay time between individual pulses. So if we don't give the material enough time to recover itself, and if we just electrically excite the material after a short period, for instance, after 100 milliseconds or 10 milliseconds or 200 milliseconds, we observed that the charge carrier dynamics are absolutely different. So actually, the very first measurement is different than the very last measurement if we don't wait long enough between the measurements. So there's a history-dependent effect for this charge carrier dynamics. And this may be particularly interesting because when you do a transport measurement, for instance, you apply a bias voltage, and this bias voltage may affect the measurement itself. So you may actually change the physical properties of the sample that you are trying to measure by just applying a bias voltage. And we also quantified this effect, and we have seen that if we have very short time delays between individual pulses, in this particular case, we measured like 10 millisecond difference between individual pulses. The effective activation barrier is monotonically increasing for the motion of charge carriers, and then this is independent of the temperature. So even at higher temperatures, which was like 75 degrees Celsius in our case, the material does not have enough time to recover itself, even with increasing temperatures. The next effect that we looked into was looking at the spatial extent of this temporal effect. Particularly, we looked into, we found two different surface spots with similar time-dependent properties, and then we increased their distance. We had like two similar stops with within the order of 400 milliseconds. And then some other spots with like 50, 100, and 300 nanometers separation between our reference points. And then we kept this delay time as a short delay time. So when we increased the spacing between two different spots, we had observed that this time-dependent and history-dependent properties has actually an extent of up to 400 nanometers. When we, in the spatial extent, in the lateral direction, and the measurement or the previous pulses affect a region with a radius of 400 nanometers, 400 nanometers. So the take-home messages for this very first part is that local variation of charge carrier dynamics is possible for materials like strontium titanate. And it was possible to get the temporal variation of vacancy dynamics by tuning the delay time between individual pulses. And then we also looked at the spatial extent, how much distance these effects are preserved by looking at the spatial extent of these temporal variations. As a spin-off of these measurements, we actually did a second set of experiments at which we excited the surface with ultraviolet irradiation. It's a very similar experiment that we excited the charge carriers within the proximity of the surface by applying an electrical pulse. However, we induced surface oxygen vacancies on titanium dioxide, and we looked at the effect of these surface oxygen vacancies for the charge carrier dynamics within the proximity of the surface. So there's an UV light that shines the surface, and then we have an electrical pulse, and we do the same thing. We just demodulate the resonance frequency shift here, and then we apply the pulse, and then here at this part, and then there is zero bias here, and we just demodulate this resonance frequency shift in order to get the effect of surface oxygen vacancies for bulk charge carrier dynamics in titanium dioxide. When we did this, we first had to conduct compare vacuum measurements with ambient measurements in order to justify that our ambient measurements are not dominated by the relaxation and motivation of surface adsorbates, and we see that they are statistically the same. The effective activation barriers of surface and bulk charge dynamics. And then when we looked at the effect of ultraviolet irradiation, we have seen that the time constants associated with charge carrier dynamics is actually decreasing with ultraviolet irradiation of the surface. So this means that when we irradiate the surface with ultraviolet light, the surface oxygen vacancies motivate the motion of bulk charge carriers. So this was an interesting result. And then we also compared quantitatively how this ultraviolet irradiation changed the effective activation barrier within the bulk system. And we have observed that the ultraviolet irradiation, which induces surface oxygen vacancies, actually makes it difficult for bulk charge carriers to move. So which was an interesting result on its own. And then we have seen that this reversible, this effect, this ultraviolet irradiation is a reversible effect. So when we stop irradiating the surface, we have seen that the effective activation barrier recovers itself as it was apparent in this time-dependent measurement as well. So when we turn off the ultraviolet irradiation, the charge carrier dynamics time constant has recovered, and we have also observed that its effective activation barrier is recovering itself within the same time frame. In addition to that, most recently we also measured on similar sample systems for their multidimensional characterization of contact potential difference measurements. Contact potential difference is simply the difference of the Fermi level of the surface as well as the scanning probe tip, which is in thermodynamic equilibrium when these two are in close proximity. And we have seen that with increasing temperature, the Fermi level shifts towards the conduction bands for intrinsically end-doped materials such as strontium titanate or titanium dioxide. So in this measurement, we actually did like force spectroscopy measurements as a function of bias voltage, and then we reconstructed tip sample interaction force for this for this individual force spectroscopy measurements, and then it was able to we were able to recover contact potential difference, which is an indication of the Fermi level of the surface, as a function of tip sample separation. And when we did so, we have observed that the contact potential difference decreases between the tip and the sample with increasing temperature, which means that the Fermi level shifts towards the conduction band for strontium titanate, which is an intrinsically end-doped material. And then when we did a similar experiment for titanium dioxide, we have seen that its Fermi level again shifts towards the conduction band. However, for gold, which is a free electron material, there's a minimal difference, there's a minimal variation of the contact potential difference, which is more clear in this aspect. So for the gold-coated silicon, which had a gold thickness of in the order of 50 nanometers, the contact potential difference was minimized compared to the other end-doped materials as a function of temperature variation. So after talking about this time-dependent and non-history-dependent aspects of my talk, I also want to say that I'm actively looking for multiple PhD students, and we will continue with, I have like 2 different projects. For my first project, we are interested in the measurement of equilibrium and non-equilibrium dynamics of vacancy migration at the nanoscale. For this project, we are looking at how the bulk and surface oxygen vacancies in titanium dioxide change the charge carrier dynamics. And then we have 2 different pathways. We will either irradiate the surface with ultraviolet irradiation, or we will change its preparation recipe in order to change the surface and bulk carrier, oxygen concentration. And we are interested in measuring the charge carrier dynamics by using techniques similar to that I have mentioned. In order to rationalize this project, we actually established a multi-million-dollar laboratory for scanning probe microscopy system at University of Quebec. So with this ultra-high vacuum, low-temperature, helium-free system, we can work uninterruptedly at less than 10 Kelvin and under ultra-high vacuum conditions. And we can do simultaneous atomic force microscopy and scanning tunneling microscopy experiments, which reveal the local electronic properties of the samples simultaneously with the same atomic tip. So if you are an interested PhD student, or if your students are interested in this type of topics, you can let them know. And for a second project, we are interested in nanoscale characterization and aim-specific design of amorphous materials. So this has absolutely nothing to do with spin or magnetic materials, but we are interested in amorphous metals. So for these amorphous metals, we want to characterize them with atomic resolution by using our brand new microscope with a chemically activated tip. So what we will do is that we will put an oxygen carbon monoxide molecule at the end of a metallic tip, and then we will do simultaneous atomic force microscopy and scanning tunneling microscopy experiments at low temperatures in order to reveal how non-crystalline materials behave. And for this project, I'm looking for 3 different PhD students and at least 2 master's students to work on this project. So again, I would like to thank organizers for giving me the opportunity to talk about my research, which had nothing to do actually with spin or spintronics or magnetic materials. But it was nice to attend this very nice conference, and I would like to, if there are some questions, I will be more than happy to answer them. Thank you.
I'm sorry, I missed the first part, so I'm sorry if I'm asking something wrong.
Sure, sure. No, no.
So, do you have ambient control in your setup?
Yes, we have ambient control in our. We have two different microscopes. In our VICO microscope, which is VICO Enviroscope system, which is the old microscope actually. We can either work under ambient conditions or we can work under vacuum conditions, but it's very mild vacuum. It's like 10 to the minus 5 millibar.
Okay, so the experiments that you performed,
yes,
the temperature-dependent experiments, were they performed under vacuum?
Strontium titanate experiments, the first experiments, they were conducted under vacuum conditions, but for titanium dioxide measurements, which we had to induce oxygen vacancies, they don't work under vacuum conditions because we need water in order to reduce surface. So they were conducted under ambient conditions, but in a controlled atmosphere.
Okay, so this comes to my actual question now. So the temperature-dependent surface potential difference that you showed, how do you make sure that it's not coming from some weird ambient effects or moisture operation or something like that? So could you comment on that?
Yes, we measured by using different types of cantilevers, and the most important part is that we are measuring the contact potential difference, not the actual Fermi level. So any change in any chemical change in the tip, which may be induced under ambient conditions, may affect the absolute value of our measurement. So we did like recycled measurements. So we measured the properties at different temperatures, and we went back to the original temperature that we measured. Also, we used different types of cantilevers. And on top of that, in order to make sure that we don't have any adsorbates on our tip or on the surface when we do these potential measurements, we looked at the energy dissipation maps of the surface, because if there are more adsorbates on the surface, the energy dissipation would have increased, and this would show up in the signal in our signal that we drive our cantilever. So this is actually a property that we can physically measure, and we measured it, and we didn't see any statistical difference when we did cyclic measurements and over the course of the measurements. So if you look at the manuscript, actually for the paper for this one, we had all energy dissipation values for the excitation for each and every single measurement, and we checked and we verified if there's any variation because of absorbates and because we applied bias voltage. So this was some potential, and we checked that. We didn't see any effect. Thank you. Thank you.